Okay, this one was quite a mess of things to deal with, so to save us time, I'm just going to dive in. The statement is, in section 11.2.1, we calculated the energy per unit time radiated by a, quote, non-relativistic point charge, the 𝘰𝘮𝑚𝑎𝑟 formula. In the same spirit, calculate the momentum per unit time radiated. Oh my goodness. Okay. Whoever first deviated or came up with this derivation, I applaud your soul and your patience because it is well above my patience grade. But yeah, let's go ahead and dive in. So the momentum flux density is minus the Maxwell stress tensor. Throw back to chapter 8. Okay. If you recall, the stress tensor had components of the form epsilon naught EI EJ minus 1/2 delta IJ E squared plus 1 over mu naught BI BJ minus 1/2 delta IJ B squared. Okay, those are the components of the tensor. But remember that the tensor was part of a larger system here. And so we say that the momentum radiated per unit retarded time is dp dtr, because we have to now take the derivative, is equal to the negative, okay, hence the negative of the Maxwell stress tensor, 1 over the retarded time with respect to the proper time of t dot dA. Here, if you recall, we proved what the ratio or the relation of the partial derivative of the retarded time is to the proper time earlier with RC over R dot U. Okay. And so here we got, if we factor a C out, we can kind of put this, we can rewrite it as such when we put the U in and then invert it. So that's what we're doing. That's what we're dealing with, and we want this because of the forms that we have in section 1.2. So this factor is 1 when V is 0, and it can be ignored in deriving the 𝘰𝑚𝑎𝑟 formula, but it does contribute to the momentum radiated. Okay, so this is why it's important. Now, this integration is over a large spherical surface centered at a charge d capital A is equal to script r squared sine theta d theta d phi in the r direction. Okay, our pretty typical coordinates there. As is the case of the power radiated, only the radiation fields contribute. E radiation is the point charge Q over 4 pi epsilon naught with all these cross terms. Again, this is not the full expression for the field of a moving point charge. We just need the radiation fields, which need the acceleration. And then B radiation is equal to 1 over C script R cross E radiation. So again, these are the radiation fields only, not the total fields. So what this tells us is that the Maxwell stress tensor taking the dot product with dA gives us this full expansion here. Okay, so it looks familiar. We lost the indices just because we're taking them as vectors, and we'll have to deal with the indices later. Here, though, note that B dot dA is equal to 0, and for radiation fields, E dot dA equals 0. You notice how, that being said, the cancellations of the R's will come through, and the integration will go bye-bye. So what we're left with here is the 1 over E squared dA and the 1 over B squared dA. Hence, we need to find what B squared is in terms of E squared. And we can do that by squaring the B, taking a dot product of the cross products. And as you see, when we do that, we can kind of distribute that dot product. So we get R cross E dot R, and then R cross E. Okay, so that's where we get the E cross R script R cross E, which is just the back cab with the dot product there. Again, vector identities, use them or lose them. Okay, so when we apply that other dot product, we get script R dot E squared, which just become, and then we get a script R. So that's where we are able to, again, be in unit vectors. Those are easy to deal with. And we are able to move to a mu naught epsilon naught E squared for your B field. So that's pretty easy. And then once we plug that in to the tensor dotted with dA, we see we get the mu's canceling as expected, and then we get a minus epsilon naught E squared dA, which is utterly useful, and we like that. We had this kind of system set up like this a few questions ago, but the double cross product will always be in this theory. So dP dTr, based on what we had, the negatives cancel and we can put the epsilon naught outside, and then we're just left with the script r dot u over script rc from the 1 over the partial of tr partial t, so we just invert it, and then e squared for the tensor and dA. So now just plug everything in that we need for the electric field. We see that script r over r dot u to the third power in the electric field cancels with the factor of the r dot u from the retarded time derivative, and we also have a factor of script r that cancels, hence why we only have script r over r dot u to the fifth instead of script r squared to the sixth. And then we just have our triple product there. Now we can expand the integrand in the first order with beta vector instead of just a regular beta for v over c, our typical substitution. And then of course with that we see that u is equal to c script r hat minus beta, because if we distribute it back in we get the script r, c script r minus v, which is our normal u. So with that we take the dot products so we can see what the heck script r dot u is. And so we know what that first term in the for the first fraction is, which just goes to 1 over script r to the fifth, c to the fifth, and then 1 plus 5 r dot beta. All right, cool enough. Now here's where the mess of the situation comes in. That triple product squared. Of course, we can use back cab rule to expand the triple product. And then we can plug in what we found with r dot a and r dot u, respectively, kind of tidy that up as much as you can. And then we end up with a RC with a bracket. But now we need to square this dang thing. So in the square, we go ahead and square the coefficients, the script r and c. But then we have to distribute everything inside, which turns into a colossal mess. Try to take it step by step just to show you where it's at, but patience only lasts so long. We see we get a couple cancellations. Very nice. And so what we actually want is the ratio of script r magnitude times this triple product squared all over the r dot u to the fifth. So here we put it all together as best we can. We see what cancels. We like that. And it's up to us now to showcase after we distribute the 1 plus 5 r dot beta into the triple product squared bracket, and we just have to reduce down. And you see we take a couple lines to get to the final line there. I'll let you read the algebra, but then after we do that, our integrand reduces to 1 over script r squared c cubed bracket r cross a squared plus r dot this 3a beta plus 2a times a dot beta minus 5 times r dot beta and r dot a squared. Whew, okay. So to integrate the first term, we set the polar axis along a, okay, since we have a cross product. That being said, the cross product has a magnitude of a squared sine squared theta. Since we're dealing with the cross product of a unit vector, its magnitude is 1 and we don't include it. So we know what r hat is in this coordinate system, which is the typical spherical coordinate for r. Again, polar axis is the z-axis, so the phi integral kills the x and y components, because anything over a full cycle of 2 pi, 0 to 2 pi, of just a cosine or sine goes to 0. So we're only concerned with the z component, and that's from 0 to pi. So clearly then, once that goes through, yeah, you see that goes to 0. Cool, we like that. Note that if v equals 0, then dp dtr is equal to 0, and a particle instantaneously at rest radiates no momentum. Makes sense. That's why we had to carry the expansion to the first order in beta. Whereas in deriving the Lamar formula, we could afford to set v equals 0. The second term is of the form r dot g. Recall what g was, the momentum density, or the constant vector. We're just going to let it be the constant vector here, not the momentum density. Setting the polar axis along g so that r hat dot g gives us g cosine theta. The x and y components, again, vanish in that nice integral. So we're left with this integral set up here, which gives us a whopping 4 pi over 3g. Okay, and then the last term involves two things, script r dot beta and script r dot a squared. This time we orient the polar axis along A, and V lies along the XZ plane. So we break down beta in terms of just two vector components, the XZ. So its dot product gives us beta x sine theta cosine phi, and beta z cosine theta. All right, makes sense based on what script R was. A squared comes out front, no big deal. That being said, let everything start calculating through as you see in the integrals, split up for component-wise. Just be very aware that this thing is not always nice to you. Script R gives us an x and y, an x and z. Y cancels in that phi, in the phi integral, so that's why we don't carry the y down from the script R hat. And then we see what we're tidied up with after the fact is 4 pi over 15 a squared beta plus 2 a dot beta a. Putting this all together now, all three terms, we see that in the squiggly brackets. We get kind of the first term goes to 0, and then we get kind of a similar square bracket, just with different coefficients out front. So we take and factor that 4 pi out, cancel it with the denominator in the first step. Then we expand that 1 over 3 or factor 1 over 3 out, since 5 times 15 is 3, or 5 over 15 is 1/3. So we get rid of that. We take care of 1 over c to the 4th by taking a c squared and putting that to mu naught epsilon naught to cancel the epsilons. But again, we have very similar terms in the square brackets, and they actually cancel, albeit we'll have to rearrange, but not too bad. And then we're just left with 3a squared beta minus a squared beta, so that leaves us with a 2a squared beta. So we can combine that down and put beta back as v over c. And the 2's cancel down with that, why are you not canceling down? That should be a 6, excuse me. But anyways, you see how after the fact, that's how we combine the momentum together, or the dpdtr with all of this. And again, if you wanted to, you could do this with the angular momentum. You would just need to take the cross product of this momentum with the radius r, with some radius function r. And that gets even worse in this derivation. So be aware. And remember that that 2 cancels with the denominator there. So it's actually mu naught q squared over 6 pi c squared a squared times v, where v is still a vector.